In this video, we discussed polynomials of one variable and the division algorithm. And this is a really important section in chapter 1 of the algebraic geometry text that we're using because it basically foreshadows a lot of what we're going to do in the next few chapters um, by specifically answering some of those interesting questions that we talked about in earlier sections for polynomials of one variable. And it turns out that a lot of the results that we're going to look at in the future are all based on the division algorithm. Now, if you've taken high school algebra, you've already used the division algorithm before. If you've ever divided a polynomial by a polynomial, all of this will be familiar to you. But I want you to think about it a little bit differently. We're putting it into a new context. And ultimately, we're going to use the division algorithm that you studied in high school to tell us something about ideals in the polynomial ring k of x. So this is really important, even though initially it might feel like you're just doing some high school algebra. You might say, why is this important? It's important because it generalizes. And there are some surprisingly deep consequences and implications of the division algorithm. So that's why we're interested in it. In this video, we're also going to define some terms. In order to talk about the division algorithm, we have to define the term, the leading term of a polynomial in that polynomial ring k of x. We will state the division algorithm in pseudocode. We will also state a proposition that just basically tells you what the division algorithm promises us. Then we will apply the division algorithm to an example. It's just going to be a high school, like college algebra type um, a long division example of dividing one polynomial by another polynomial. But when we see that in practice, we'll be able to make a little bit more sense out of that pseudocode that we will have already discussed. And then we'll look at one implication of the algorithm. Actually, what we're going to do is we're going to prove that if k is a field and f is some non-zero polynomial, then f has at most degree f roots in that field. And we actually used that result back in section 1.1 when we proved proposition 5. So we didn't really prove it. We said it was based on this fact that we just took to be true. But in this section, we're finally going to prove that that's true. And it turns out that we can prove that that's true once we have the division algorithm under our belt. So let's start with this definition of a leading term. If we have a non-zero polynomial in our polynomial ring k of x, so that means the coefficients of that polynomial are in the field k, and this is a polynomial in one variable x. Given that, let's say that f is equal to this. A naught times x to the m plus a sub 1 times x to the m minus 1 plus a sub 2 times x to the m minus 2, and so on. Go all the way down to a sub m. So this is m terms. The highest power of x here is that mth power. Here, all of the a sub i's are in our field k. And our leading coefficient, a sub 0, is not equal to 0. If our a sub 0 is not equal to 0, that means this is the highest degree term on this list. And if this is the highest degree term on that list, that means the degree of f is that exponent. So the degree of f is m. If this is the structure of f, then we're going to say that a sub 0 times x to the m is the leading term of f. And we'll notate that this way. Okay, so that's our definition of a leading term. Now, one other thing that we need to, or that we're going to use later, is a fact about polynomials f and g. So if f and g are non-zero polynomials in our polynomial ring k of x, then if the degree of f is less than or equal to the degree of g, then the leading term of f divides the leading term of g. And it actually goes both ways. If the leading term of f divides the leading term of g, then this is also true. So this implies this, and this implies this. Now, if you don't remember what divides means, just remember that that means this is a factor of this guy. So in other words, we could say that the leading term of g is equal to the leading term of f times some other polynomial in our polynomial ring k of x. So that's multiplication. And I think that that makes sense. If the degree of this polynomial is less than the degree of this polynomial. So I've got like a sub 0 times x to some power. And then this one has a leading term that maybe looks like b sub 0 times x to a different power. The a sub 0 and the b sub 0 really don't make a difference. When it comes to the degree, if we're saying that the degree of g is greater than the degree of f, we're just saying that that highest power of x for g is larger than the highest power of x in the polynomial f. So this is just saying that if that's the case, then the leading term of g is equal to the leading term of f times some other polynomial. And I think that makes sense. If this, if the degree of g was 5, let's say, and the degree of f was 3, well, this would be a constant times x to the 5th for its leading term, and this polynomial would have a constant times x to the 3rd for its leading term. I would just need to multiply by a constant times x squared, multiply this guy by a constant times x squared in order to get that one. That works. As long as this degree is smaller, I can just multiply by a constant times x to the appropriate power to make the degree of the result equal to the degree of the leading term of g. So that's what that says. And I'm writing that down there because we're going to need it when we prove the division algorithm in just a moment. So now we have this notion of a leading term, which if you've ever divided polynomials, you know is really important. And then we have this fact, which will be really important in our proof of the division algorithm. And here is the division algorithm itself. This is proposition 2 in our book. This is the division algorithm for functions of one variable, or for polynomials. Let's just say polynomials in k of x, which just means that they're polynomials of one variable. It says, let k be a field. And remember what that means. It means all the usual things are possible. So we can add, subtract, multiply, and divide in that field. And let's say that g is a polynomial in k of x. G is not the zero polynomial. And we want the degree of g to be less than or equal to the degree of f. Now this was not stated in the proposition in the book, but it's required. If you look at this result, the rest of this will not make sense unless the degree of g is less than or equal to the degree of f. Given that, then every polynomial f in k of x can be written in the following way. So f can be written as q times g plus r, where q and r are polynomials, and either r is equal to the zero polynomial does not have a degree, or the degree of r is less than the degree of g. And then the proposition in the book says, furthermore, q and r are unique, and there is an algorithm for finding q and r. And we call that algorithm the division algorithm. This basically says we can take any polynomial, and if we have a polynomial of lower degree, that polynomial can be written as q times that polynomial of lower degree plus some other polynomial. These choice of letters, it's not accidental, it's insightful. If we take f and we divide it by g, what we'll see is this. So if f is q times g plus r, we take everything and divide by g. You can take each term and divide by g. The g's cancel. And what you see is that f divided by g is q plus r over g. Or in other words, q is the quotient when we take f and divide it by g. And r is the remainder when we take f and we divide it by g. So the choice of letters actually makes a lot of sense. Now I'm going to write down the pseudocode for the division algorithm, and then we will actually prove this result. You might think, well, why does that even matter? Why is that so powerful? Well, there are just so many implications of this algorithm, and we're going to talk about that later. But what this says is if you have any polynomial f and a lower degree polynomial g, there's a quotient out there, so that you take that quotient and you multiply by g and you add the remainder, and that's going to give you your f back. And that remainder will always have a degree that's lower than g, that polynomial that you were dividing by in the first place. This is provided that we're working with polynomials with coefficients in a field k. So we're going to show that that's actually true, that any f can be written in this form. We're going to make sure that the algorithm terminates, so it actually eventually gets to some result, because it says that there's an algorithm for finding q and r. We're going to show that q and r are unique, and we're going to show that q and r are going to satisfy this last piece if we follow the algorithm. So let's look at the division algorithm itself in pseudocode. I don't want you to be intimidated by pseudocode. It's actually a lot like a recipe. You're just going to follow the directions. Did I spell algorithm right? There we go, HM. All right, pseudocode for the division algorithm. So we're going to start with G and F. Degree of G has to be less than the degree of F. And our output will eventually be a quotient and a remainder. So we're basically taking F and we're dividing it by G, and we're saying, well, what's the quotient have to be? What does the remainder have to be? Well, in order to figure out what that quotient and remainder would be, initially we set Q equal to 0, and we set the remainder equal to F. And then we just proceed through this while do object. So we'll say while r is not equal to 0 and the leading term of G divides the leading term of r. Or in other words, while the leading term of r, or while the polynomial r has a degree larger than g. So the degree of r is greater than the degree of g while that's happening. Let's do the following. You're going to take your old q, you're going to replace it with this new q. The new q is the old q plus the leading term of r divided by the leading term of g. And then after you do that, your new r is going to be your old r minus the leading term of r divided by the leading term of g times g. Now this looks a little cryptic. At first you might say, what on earth does that mean? But this is the division algorithm. This is exactly the same algorithm that you followed if you learned how to divide a polynomial by a polynomial in your college algebra class or your pre-calculus class. That's all this is. And I'm going to walk you through it, and we're going to show how this is actually getting us to that result that we saw on the previous page. And what's nice about this pseudocode too, and a lot of the pseudocode shown in our textbook, that material that we're studying, that's Ideals, Varieties, and Algorithms by Cox, Little, and O'Shea, is that if you have any programming experience, you can use Maple or Mathematica or anything, and you can use this little bit of pseudocode in order to do the division, so you don't have to do it all by hand all the time. Most of the time we aren't doing these things by hand, but it's important to understand what that computer is doing. We don't want it to be a black box. Okay. So here's the plan. So we're going to do a few things. We're going to show first that the final q and r have the desired properties when we follow this algorithm. We're going to show that the algorithm terminates. Terminates. In other words, this part here eventually becomes false. And then we will actually work through an example. And I'm actually following the order that's just exactly the same order as provided in the textbook. And then after we do our example, we're going to show that Q and R are unique. And I really like the discussion. I like this book a lot. So I'm going to stick to their outline here because I think it's really good. I think it's well done. All right, first let's show that Q and R have the desired properties. Well, in order to show that, we need to note that the fact that Q or F is equal to Q times G plus R, this holds the whole time. That's our first note. So it holds initially, and it remains true as we redefine Q and R. So let's say at the very beginning, what do we have? Initially, we have F equals Q, which is initially defined to be 0, times G plus R, which is initially defined to be F. Okay, so of course, F is equal to F. Now, as we redefine Q and redefine R, this is what's going to happen. So if we have f here, it's supposed to be q times g plus the remainder. The q will be replaced by the old q plus the leading term of r divided by the leading term of g. I'm going to take that, we're going to multiply by g. Then we're going to add the remainder. And remember, our remainder is updating as well. The remainder is the old remainder minus the leading term of r divided by the leading term of g times g. This is just algebra, nothing fancy. If you distribute, you can see we got q times g, whoops, g, not q, times the leading term of r over the leading term of g times g plus r minus this exact same expression here. So those undo each other. And what we get is this times this plus r. All right, so keeping that in mind, let's show that the final q and r have the desired properties. Or actually, let's show that the algorithm terminates. So first of all, the algorithm terminates under these conditions when this is false. So the algorithm is going to terminate when r is equal to 0. When r is equal to 0, or this is no longer true. Well, if the leading term of g divides the leading term of r, that means the degree of r is greater than the degree of g. Or actually, it's going to be greater than or equal to, excuse me. If this is not true, that means r is equal to 0 or the degree of r is less than the degree of g. And look at what this says. The division algorithm says that every f can be written in this form where q and f, or excuse me, q and r are A-R-E-R, polynomials, and either r is equal to 0 or this is true. And yes, that is going to be the case when the algorithm terminates. So we have this. Now, you might say to yourself, how do you know that this will eventually happen? The way that we know that this will eventually happen is by looking at the definition of r. So our r is this. Our new r is the old r minus the leading term of r divided by the leading term of g divided by g. Now, if I do this, if I take my old r and I subtract this, it turns out that this result will either be 0 or it will have a degree that's smaller than the previous r. So you might think of this as, even though we have r on both sides here, I know some students are like, oh, it's the same expression. No, it's not. This is like the old r. That's your new r. So we'll say that the degree of the new r is going to be less than the degree of the old r. I know we should probably use something other than new and old, but you get the idea. I think it makes it very concrete for you that we're just, if we do this, then r is either going to be 0 or this is true. Now let's actually check that out. Don't just take my word for it. Let's see why that would be true. In order to make this more concrete, let's let r be a polynomial. Let's write it this way. Say its coefficients are given by a sub I. I goes from 1 through m. And g will have coefficients that are b's. And we'll let b go, or the b sub i's be the coefficients, and we'll let those i's go from 1 through k. Now, if this algorithm is running, the leading term of g divides the leading term of r. So that means the degree of g is still less than or equal to the degree of r. So that means if we are here, if we're about to apply this, so we only apply this if this is still true, then that means that k has to be greater than m. Or excuse me, I'm sorry. The degree of g is less than or equal to the degree of r. So m has to be greater than k. At least while the algorithm is still going. Well, in that case, if I look at these two, the leading term of r is this guy, and the leading term of g is this guy. So leading term of r divided by leading term of g is this. We're going to have a sub 0 divided by b sub 0. And then x to the m over x to the k, we'll subtract those exponents and we'll have this. Since m is larger than k, m minus k is going to be positive. So this is a monomial, and this is just x to some power, x to some positive integer power. Okay, if this is true and this is true, in that case, let's check this out. Let's see what happens. Our new r is equal to the old r, which was a sub 0 times x to the m, and so on, minus the leading term of r divided by the leading term of g times g. Well, g is this b sub 0 times x to the k, and so on, and see what happens. This is actually equal to that. Now, if you multiply these two together, I actually had the leading term of g in the denominator, and the leading term of g was right here. When we multiply those together, we're going to have a negative leading term of r. So you're going to have a leading term of r over here and a leading term of r over there. And no matter what else happens, those are going to cancel out. And so the degree of this guy has to be less than or equal to the degree of the original, unless everything happens to cancel out and the new r is 0. Okay, if that's the case, then every single time you go through this algorithm, the degree of r is dropping. So it drops and it drops and it drops, and started with integer values, or positive integer values for these degrees, because we're talking about polynomials. Eventually, it's going to run out of times to drop. It's going to drop a finite number of times, and the algorithm must terminate. So it's going to drop a finite number of times until either r is, or until this is not true, which means that r is equal to 0, or the degree of r is less than the degree of g, and that means that the algorithm terminates. Okay, terminates. So what do we have? The final q and r have the desired properties, yes. The algorithm terminates. Eventually this becomes false, yes. We want to show that r and q are unique. We're going to do that in a little bit, but first I want to do an example, just to make sure that you understand what this is saying. If you've ever done this, if you've ever divided polynomials in pre-calculus, you've done this before, but I want you to see sort of in practice what this means. So let's say we're starting with this polynomial. F is equal to 4x cubed minus 7x squared plus 3. And g is equal to 2x plus 1. We want to show that f is equal to q times g plus r, where either r equals 0 or the degree of r is less than the degree of g. And notice right away that the degree of g is less than or equal to the degree of f, so we can actually do this. Let's apply that algorithm here. We're applying that guy right there to this guy. That's a bit of a distraction, so I'm going to fold that, get that out of the way. Okay, so we're here. All right, so what this says is initially set your quotient equal to 0 and your r equal to the function f. And I'm going to put a little 0 on this, q naught, like that's our initial q. I'm going to call it r naught. Our initial r is f. And I'm just going to do the long division just like I would in pre-calculus. Now in pre-calculus, we need all of the powers of x, starting with the highest power of x. We don't want any missing powers. So I would call this 4x cubed minus 7x squared. There's no x term, so I'm going to add in a 0x as a placeholder, plus 3. And I'm going to keep a running list of my quotients and my remainders. If you're saying to yourself, it's not a remainder, how can that be a remainder? You're right, it's not the final remainder. But eventually that remainder is going to become the remainder that we're talking about by following this little algorithm. Okay, so this says, while r is not equal to 0 and the leading term of g divides the leading term of r, do this. Let's check it out. The leading term of g, that's 2x. Saying while this divides the leading term of r, the leading term of r is right here, because remember r and f are the same thing at first. So we've got this 2x and the 4x cubed. So they're saying while this is true, while r is non-zero and it's not 0, and this divides this, that checks out, set the quotient equal to the old quotient, which was 0, plus the leading term of r, that's this, divided by the leading term of g. You've done this before. Again, if you were doing this problem in college algebra, I would say to you, focus on this term and this term, and you'd say to yourself, 2x times what gives us 4x cubed? Well, 2x times 2x squared would give us 4x cubed. So I would let my new q equal 2x cubed, or sorry, 2x squared, because 2x squared times 2x gives me 2 times 2 is 4, x squared times x is x cubed, so that gives me that. And then the next thing I would do is I would take this and I would multiply by this. We're going to multiply everything over here by that. So we're going to distribute. Got this times this is 4x cubed by design. 2x squared times positive 1 is going to be positive 2x squared. And then we're subtracting this polynomial from that polynomial. So what I tell my students is to just change the signs and then add like terms in the columns. Now, some teachers really hate that there are two, it looks like there are two operations there. If you want, you can add some parentheses. We've got negative 7x squared minus 2x squared, that's negative 9x squared. And you could bring everything else down if you want to. And then the 4x cubed minus the 4x cubed, those are gone by design. I claim this is my new remainder. Now let's check it out, make sure that that's actually what this algorithm told us to do. So the algorithm says, while this is true, which is while the degree of r is less than or equal to, or greater than or equal to the degree of g, and initially this was our r. This is degree 3, that is degree 1, so that is satisfied. Do this. It says, take the old quotient, and then add the leading term of r divided by the leading term of g. Well, the leading term of r is this. This divided by this is that 2x squared. So we're saying, take the original q and add this divided by this. 4x cubed divided by 2x is 2x squared. Good. And then we said, okay, that's our new quotient. And then we said, okay, now take this leading term of r divided by leading term of g. That's this guy up here. And multiply it by g. So we're just taking this and multiplying by all of that, and then subtract it from the original r. This was our r. We did this times this, which is here, and then we subtracted those and we got that. And so this is our new r. So the algorithm here in the pseudocode is telling us to do exactly what we know to do from our pre-calculus classes. So we keep going. I've got a 2x here and a 9x squared. The degree here is greater than the degree here, so I'm going to keep going. And I ask myself, 2x times what gives me 9x squared? Or alternatively, what is 9x squared divided by 2x? What's the leading term of r divided by the leading term of g? Well, the leading term of r divided by the leading term of g is negative 9 over 2 times x. You can also ask yourself, negative, or this times what will give me this? 2x times negative 9 over 2 times x. The 2's will reduce. We'll end up with a negative 9. X times x is going to give me an x squared. We're going to get exactly the right thing. So that goes into our quotient. Notice that our quotient is being updated as the original quotient, the quotient from last time, plus the leading term of r divided by the leading term of g. That's this piece right here. And now we're going to multiply, not all of it, just this piece times g. That's this right here. And then we're going to subtract that result from the r that's there. That's what that tells us to do. So we have this times this is negative 9x squared by design. And then that times a positive 1 is itself. And then we're subtracting polynomials. So you want to change the signs and then add like terms in the columns. Those guys are gone. We're going to have a 9 over 2 times x here, plus 3 there. And that means that's our new remainder. And then we look at the degree of this remainder and the degree of g. This is degree 1 and that's degree 1. So the degree of r is still greater than or equal to the degree of g. They're equal to each other. So we're going to do this one more time. We say to ourselves, this times what gives us this, which gives us a 9 over 4. Or alternatively, you can say this divided by this gives me what? What's the leading term of r divided by the leading term of g? It turns out to be 9 over 4. If you multiply these guys together now, this times the entire g, and that's what our algorithm tells us to do. We've got 9 over 4 times 2x is 9 over 2x. And then 9 over 4 times positive 1 is 9 over 4. And we're subtracting polynomials. So we change all the signs on the second one. If you prefer, you can put parentheses there. Some people are like, you can't have two operations there. We're adding a negative. Think of it that way. And then you add like terms in the columns. These guys are gone, and we end up with 3 minus 9 over 4, or 12 over 4 minus 9 over 4, which is 3 over 4. And then we look at this. Our new quotient is this. And our new remainder is this 3/4. And we compare these guys. Say the degree of this is 0, the degree of this is 1. The leading term of g does not divide the leading term of r anymore, because the degree of this is smaller than the degree of this. So the algorithm terminates. This is our final r. This is our final Q. And this tells us that f divided by g, 4x cubed minus 7x squared plus 3 divided by 2x plus 1 is equal to the quotient plus the remainder over the divisor, or over that g. And if you multiply both sides of this equation by g, you get f equals your quotient, and then this did not have that there. So when we take this and multiply by that, we'll get the quotient times g. And then when we multiply this guy by 2x plus 1, that reduces, and we just have plus the remainder. This is f equals q times g plus r. And let's see, what were the requirements? F is equal to this, where q and r are polynomials, they are, and either r is equal to 0 or r is less than, or the degree of r is less than the degree of g. And this is a constant, so it has degree 0. That is linear polynomials, it has degree 1. So the degree of this is less than the degree of that. Now the claim is that these are actually equal to each other. If you want, you can check it out. I'm not going to prove that here, but if you distribute this binomial times that trinomial and then you add the 3/4, I guarantee you're going to get this, provided I didn't make any arithmetic mistakes or algebra mistakes as we went through that process. So even though this looks a little foreign, perhaps, you've maybe never seen anything like this before, this is doing exactly what we studied in our pre-calculus classes. This leading term of r divided by leading term of g is what we do every time we look at this and we ask ourselves, 2x times what will give us 4x cubed? 2x times what will give us the 9 over 2 times x? Or 2x times what would give us this? Well, that's not possible, so we stop. And I missed that one. So these guys come from taking this and dividing by this, or taking this and dividing by that, and taking this and dividing by that. And that is our leading term of r divided by leading term of g. And this quotient is being built, started with 0. It was being built a term at a time. So we did this once and we got this guy. And then we took the old quotient and then we did it again. And then we took the old quotient and we did it again until this statement was no longer true. And then with the r's, we started with this r, and then we took this guy times this guy, put that down here. That's our leading term of r divided by leading term of g times g, and we subtracted, and that gave us a new r. And then we did it again. We take this new r, and then we take our new piece of the quotient, the leading term of r divided by the leading term of g, multiply by g and subtract, and you get this r, and so on, and so on, and so on. So that's what this says, even though it looks a little odd, or it may look odd to people who aren't used to looking at pseudocode. But yeah, that's exactly what we did in pre-calculus. So this is nothing new. But what's interesting is that there are implications for ideals, there are implications for algebra, implications for algebraic geometry, there are geometric implications for all the results that we're going to prove about ideals later. But yeah, this is a very, very powerful thing that we have just outlined. I know initially it may not seem that powerful. It might seem like, isn't this pre-calculus you're teaching me? It's a foundational idea that's going to allow us to prove many other very interesting and rich results. So we talked about this and this and this. We looked at the example. What other thing that we want to do? Oh, I wanted to show you that Q and R are unique. And then we would look at the implication related to that result that we proved, that we almost proved back in section 1.1. So now let's prove that Q and R are unique. And say lastly, it's really before we move on to the next topic, let's show that Q and R are unique. Well, let's say that F can be written in two ways. Let's say that F can be written as q times g plus r, and it can be written as q prime times g plus r prime. Now those are not derivatives, those are just different q's, and it's a different q and a different r from this q and that r. That is not a derivative of anything, so please don't think of it in terms of derivatives. So let's say that these are just two different forms of the results that we would get from the division algorithm. We want to show that q has to equal q prime and that r has to equal r prime. Now, in both cases, if this is the result of the division algorithm, the degree of r and the degree of r prime both have to have degree less than g. Again, those are not derivatives. Okay. So one of those is true. Now let's say that they're not equal to each other. If r and r prime are not equal to each other, then if the degree of r is less than the degree of g and the degree of r prime is less than the degree of g, then if I subtract them, certainly that polynomial must have degree less than g. But then notice that this is also true. So that's our first note. Look at our second note. Since f is equal to both of these guys, you can almost leave f out and think of this as an equation. We could subtract this term from both sides and subtract that term from both sides. So we'll have q times g minus q prime times g equals r prime minus r, and we can factor out the g if we want to. So according to this, r minus r prime must be equal to this. Well, this is a product of two polynomials. So that would imply that the degree of r minus r, or r prime minus r, is equal to, well, the degree of this first piece, q minus q prime, plus the degree of g, and q minus q prime, if r is not equal to r prime, well then this does not, or this is not 0. And if this is not 0, that means this is not 0. So this sum of 2 degrees must be greater than or equal to just the degree of g by itself. Well, wait a minute. We just said two things that are contradictory. We said from up here, because this is required, because we require the degree of r and the degree of r prime to both have degree less than g, we must have that the degree of r prime minus r is less than the degree of g. Just taking those two polynomials, we subtract them. If this one has a lower degree than g, and so does this one, when you subtract them, it would still have a degree that's less than g. Then we're saying here, but if f is equal to this, and we're still assuming that r and r prime are not the same. If r and r prime are not the same, so that we're not talking about the 0 polynomial, so this actually has a degree, then if r minus, or r prime minus r is equal to this product, then this would have to equal the degree of some polynomial plus the degree of g, which would be greater than or equal to the degree of g. And this is the key piece. We're saying that the degree of r minus r prime is greater than or equal to the degree of g. But up here we said that it had to be strictly less than that. They can't both be true. So that's a contradiction. Dr. Redner at the University of Tulsa would go like this. Contradiction. Put a little arrow. I think it's kind of fun to draw that little arrow. So that means that our initial assumption that led us to this point must be false. So r must not be equal to r prime. I don't know if I said that right. The fact that r is not equal to r prime must be false. So that means r must be equal to r prime. And if r is equal to r prime, then q must be equal to q prime, because we know that g is not 0, right? Oops, it's a q. And that means our q and our r are unique. So if you do this division algorithm and you find that f is equal to q times g plus r, there's only one q that you're getting. There's only one r that you're getting. You're not going to do this a different time or in a different way or in a different order somehow and get a different result for q. I can't imagine how you could take this algorithm, get two different results, but yeah, this proves it. You're only going to get you're going to get one q and one r, and that's going to be unique. All right, so that is our division algorithm, which has implications for ideals in the polynomial ring K of X. But here's our first implication. Now, back in section 1.1, we proved a result, and it was based on this corollary. It said that if K is a field, and we're talking about a polynomial in one variable, f, and that's a non-zero polynomial. Then f has at most degree f roots in the field K. Now, in the proof of proposition 5 in section 1.1, we used this idea and we said, oh, obviously that's true. We remember that that's true. We know that that's true. And then we just used that fact. So we really didn't prove that result, proposition 5 in section 1.1, because it was all based on this idea that we just took for granted and perhaps we shouldn't have. But at the time, we didn't have the tools to prove that this is true. Now we have the tools to prove this is true because the division algorithm allows us to prove that this is true. So what we're going to do is we're going to use a proof by induction. And the induction is on the degree of the polynomial f. Okay. So let's say, first of all, that m, that's the degree of the polynomial f. Just for our first case, let's say that m is equal to 0. In that case, if m is equal to 0, f is a 0th degree polynomial and it's a non-zero polynomial, then that means that f is equal to a constant. Some constant in the field K, and that constant is not equal to 0. So just like, for example, if you want just to have this in your head, like f equals 5. Look what it is we're trying to prove. We're trying to prove that if K is a field and we're dealing with a polynomial with coefficients in that field K, and these are polynomials of a single variable and it's a non-zero polynomial, then f has at most degree f roots in the field K. Given that we've said that m is the degree of f, we're saying this has at most m roots in the field K. Well, if we're talking about m equals 0, obviously f has at most 0 roots in the field K. That makes sense. We're not going to have any zeros of this if f is a constant and that constant is not 0. There's no way that 5 is ever going to equal 0. So then in this case, the corollary is obviously true. Now, the way induction works, and I know we talked about this in another video, but I want to just touch on it again, is usually we show that the original statement is true for some value of n or m. In this case, we're using m. And then we're going to say that, I'm going to call this PMI. The way this works is that you show it's true for some value. So usually we use n, but this time we're using m. In our case, we're using m equals 0. So we've shown that that's true. Now, then the next thing you want to do is that you want to show that if the statement is true, I'm going to call it the statement P. If P is true for m, then P must be true for m plus 1. Now, a lot of students who are new to proof might think of this as very cryptic, but what we're saying here is that if m is the degree of the polynomial, we want to show here that if this is true for degree m, for polynomials of degree m, then it has to be true for polynomials of degree m plus 1. So if this is true for polynomials of degree 5, then it must be true for polynomials of degree 6. And if it's true for polynomials of degree 6, it must be true for polynomials of degree 7, and so on and so on and so on. It's these two pieces together that allow you to prove it for all m, starting with this one going forward, just to infinity. It's like it is a countable infinity, just starting here and then just going on forever, just one step at a time, one integer m at a time. Or one whole number m at a time. Okay, so if you can show that it's true for one particular value of m, and you can show that if it's true for m, then it must be true for, the statement must be true for m plus 1, then you're showing it's true for m equals 0, and m equals 1, and m equals 2, and m equals 3, and so on forever. So then we're showing that it's true in general. That's the principle of mathematical induction, which I'm calling PMI. Okay, so we just did the first one. 5 is never 0. This non-zero constant is obviously never 0. So obviously f has at most 0 roots in our field k. Now we want to assume that this statement is true. Our corollary is true. This is what we're trying to prove for polynomials of degree m. And we're saying if that's true, if it's true for polynomials of degree m, then we want to show that it's also true for polynomials of degree m plus 1. So we're going to assume that k is a field, f is a non-zero polynomial, let's say, actually, let me say it differently. We'll assume that if k is a field, f is a polynomial with coefficients in the field k, polynomial in one variable with coefficients in the field k, and f is not the 0 polynomial. Then it's known that f has at most m roots in k. Now let's consider a new function g. So we want g to be a polynomial in that polynomial ring as well. But this time, we want g to have degree, not m, but m plus 1. Well, if g has degree m plus 1 and g has no roots in the field k, field K. Obviously, if it has no roots, it has at most m+1 roots in the field K. It has at most degree G roots in the field K. So if G has no roots, then the corollary holds. Now, some students may not be familiar with this terminology. We talk about zeros of polynomials. Those are x values, if we're talking about polynomials of one variable, that cause the y values of that, or the y value of that polynomial to be 0. Zeros of a polynomial and roots of a polynomial, all of those are the same thing. So this is saying that if we're talking about a polynomial in this field, or a polynomial with coefficients in the field K, it has at most degree f roots in the field K. So if it's a second degree polynomial, it has at most 2 roots. If it's a third degree polynomial, it has at most 3 roots. If it's a fifth degree polynomial, it has at most 5 roots. If it's an mth degree polynomial, it has at most m roots. And if you're thinking about this graphically, you're talking about the number of times that polynomial is crossing the x-axis. So if it's a 4th degree polynomial, it has at most 4 roots. Just for example, that's what we're talking about here. Okay, so now we're saying that, let's say that that fact is true for polynomials of degree m. So we're saying if K is a field and f is a polynomial in this polynomial ring, f is not the 0 polynomial, then f has at most m roots in K. Now let's look at a polynomial of degree m+1. If that polynomial has no roots, obviously 0 is less than m+1, so the corollary holds. Now let's suppose it actually does have a 0. So those are the two cases. Either it has no roots or it has one. Has a root or a 0. At x equals a, then what that means is that g of a is equal to 0. Where a is a number in our field K. Now, because of the division algorithm, we could take our polynomial g and we could divide it by x minus a. That's going to be given by q times x minus a plus r, all divided by x minus a, or you can call it the quotient plus the remainder over the divisor. Or if you prefer, you can say that g is equal to q times x minus a plus r. Now, the division algorithm tells us that this is true. Since we're dividing by x minus a and that has degree 1, r has to have degree 0. Remember, this is where r is equal to 0 or the degree of r is less than the degree of whatever it was that we were dividing by. In this case, we're dividing by x minus a, and the degree of x minus a is just 1. So either r equals 0 or r has degree less than 1, which means that r has degree 0. And that means that r is a non-zero constant. So either r is equal to 0 or r is a non-zero constant. Either way, r is a constant from this due to the division algorithm. Well, we know that a is a 0 of g, so if we substitute x equals a on both sides, we have g of a equals q of a times x minus a plus r. course, a minus a is 0. So we have g of a is equal to r. But g of a is equal to 0 because a was supposed to be a 0 of the polynomial g. A is a root or a 0 of the polynomial g. So if that's the case, what this is saying is that r has to be equal to 0. And if r is equal to 0, that means our polynomial g is actually equal to some quotient times x minus a. Now this polynomial g, has degree m plus 1. If g has degree m plus 1 and x minus a has degree 1, then that means that q must have degree m. Now, since q is a polynomial of degree m, remember what our assumption was. That if we have a polynomial and it's a non-zero polynomial, it has at most m roots in k. So if q has degree m, then q has at most m roots in k by our assumption for this part 2 of our principle of mathematical induction proof. Okay, so q has at most m roots in k, x minus a clearly has 1 root, x equals a. So g will have the number of roots given by this guy plus the number of roots given by this guy. So that means that g has at most this m roots plus the 1 root that comes from that in k. Okay, now if you're like, what was that about? Let's go through that one more time. So the corollary says that k is a field, and we're talking about polynomials with coefficients in that field. And these are non-zero polynomials. Then that non-zero polynomial will have at most degree f roots in the field k. So 4th degree polynomial has at most 4 roots. 5th degree polynomial has at most 5 roots. And the way we proved that is we proved it by induction on the degree of f. So first we said, what if we're talking about a degree 0 polynomial? So just a constant. Obviously, it has at most 0 roots. Makes sense. Then we said, okay, let's say that this is true if you have m roots. So almost, if you want to, you can pick a concrete value of m. Let's say this is m, where m is the degree of f. Let's say that we've got a 3rd degree polynomial, and we said it's true. This is true for all 3rd degree polynomials. If it's true for all 3rd degree polynomials, does that mean that it's true for all 4th degree polynomials? Then we said yes. If it is true for m, or for mth degree polynomials, it's also true for m plus 1th degree polynomials, and this is where we proved that. So if it's true, and then remember where we started by proving it was true for m equals 0. And then this said if it's true for m equals 0, it's going to be true for m equals 1. And if it's true for m equals 1, it's going to be true for m equals 2. If it's going to be true for m equals 2, it's true for m equals 3, and so on forever. So in general, if k is a field and f is a polynomial in one variable with coefficients in that field, and f is non-zero, then f will have at most degree f roots in that field. And we proved that by induction on the field, or on the degree of the polynomial f. Now remember, we used this earlier when we were proving a result in section 1.1. We almost proved it. We We stated our result on the basis of this fact that we were not able to prove earlier, but now we're able to prove it because of the division algorithm. The division algorithm allowed us to write this G in this form. Now that we have the division algorithm, we were able to come up with this result about the roots, or the number of roots of a polynomial and its relationship to the degree of the polynomial. But this was the proposition from section 1.1 that we proved earlier. We said that if K is an infinite field, and F is a polynomial in n variables, x sub 1 through x sub n, with coefficients in the field K, then F is the zero polynomial in that polynomial ring if and only if F is the zero function Now, we're saying that F is the zero function. That means that no matter what you plug in from that n-dimensional affine space, you're going to get 0 all the time. This is f of a equals 0. That upside down a means for all a in n-dimensional affine space. And this is saying that f is the 0 polynomial that's equivalent to saying that f is equal to this sum where all the a sub alphas are equal to 0. Okay, if K is an infinite field and F is a polynomial in n-dimensional, or in n variables x sub 1 through x sub n with coefficients in the field K, then if F is the 0 polynomial, F is the 0 function. If F is the 0 function, F is the 0 polynomial. It goes both ways. We were able to prove that based on the fact that if we were dealing with polynomials in a single variable x, then F would have at most degree F roots in that field. That result here was based on the corollary. Okay, now later we restated this. Once we had the language of ideals, we stated this idea that being a 0 polynomial and a 0 function are interchangeable as long as our field K is infinite. We restated it in a different way using our new language of ideals. What I just said up there is equivalent to saying this. Now, as we learn more abstract mathematics, we're going to see like things seem to get simpler and simpler, and you're just like, oh, it's the ideal of all of n-dimensional affine space. Of course, it's 0. But this means this. That's what this means. Let's dissect this a little bit more. Remember what the ideal of a variety is. And here our variety is all of n-dimensional affine space. The ideal of a variety is a set of polynomials in n variables x sub 1 through x sub n with coefficients in K, such that f of a is equal to 0 for all a in the variety. In this case, for our variety is all of n-dimensional affine space. So this is saying, what is the set of polynomials? Give me the complete set of polynomials that are equal to 0 for all a values in n-dimensional affine space. Well, this result said that if we're talking about 0 polynomials, and that's what this is, or 0 functions, excuse me, that's what this is, well then that function f has to be the 0 polynomial. This implies this, and this implies this. That's what the if and only if means. I did not misspell if. That is the way we say if and only if. And if you want to know how to represent that in symbols, you don't even want to write IFF. You want to be even faster. You can draw this arrow with the two, like the double-headed arrow. this implies this, and this implies this. That's what that says. Or you can say if and only if. Okay, so this says the set of all polynomials that are equal to 0 for all of n-dimensional affine space consists of a single function, and it's the 0 polynomial. But that's only true when k is infinite. And again, that was based on the fact that we have at most, or a polynomial has at most its degree number of roots in k. Okay, so that's it for our discussion of the division algorithm and its implications, at least for right now. We've talked about one implication, be able to prove that result that we needed earlier. But next time, we're going to talk about implications for ideals in the polynomial ring k of x. So we're going to be dealing with polynomials in one variable, and you might say to yourself, well, what are the ideals in this space of polynomials of one variable, this polynomial ring k of x? What do those ideals look like? It turns out the division algorithm is going to allow us to answer that question. And I'll give you a hint. It has to do with the greatest common divisor of polynomials. So I'll see you next time, and we'll talk about how the division algorithm allows us to find the structure of ideals in the polynomial ring k of x.